Hello everyone, and welcome to Compressed Air Introductory Training for Energy Efficiency. My name is Punit Shetty, and I am Principal Consultant at Alliance for Manufacturing and Technology. Over the past couple of years, I have been researching compressed air system and working closely with small and mid-sized manufacturers to better understand their operational and energy challenges. And I have developed this training based on the work to help teams identify practical opportunities for improvement. This training is designed for all levels, and the goal is to help you understand compressed air as a system, not just as a compressor sitting in a mechanical room. Compressed air is used everywhere in industrial facilities. It supports tools, automation valves, material handling, packaging, and many other critical operations. In many plants, production simply cannot run without it. But compressed air is also one of the most expensive utilities in a facility. It requires a significant amount of electricity to produce, and inefficiencies often go unnoticed because the cost is hidden within the electric bill. In this session, we will focus on most important things you should recognize: how compressed air works, where inefficiencies typically occur, and what best practices help reduce energy waste while improving reliability. As we move through the training, you will also complete a 10-question self-assessment. This will help you benchmark your current system and identify the highest priority improvement opportunities. If you don't already have the worksheet, please take a moment now to download and print it out so you can score your system throughout the training. The objective is simple. By the end of this session, you should be able to look at your compressed air system differently, not just as equipment, but as managed energy system. Here's the agenda for the training. We will begin with the objectives and a short introduction to why compressed air matters. Then we will go through compressor basics, demand and distribution, air quality and reliability, controls, audit and efficiency, cost, incentives and maintenance, awareness and sustainability, and finally the self-assessment wrap-up. This is structured to follow the airflow from supply to demand. If you're watching this recording in a facility context, you may want to have a notebook or a sheet of paper nearby because the self-assessment questions will help you score your current system. Even if you don't know all the answers today, the questions will help you identify what data you need and what to look for next time you walk through the system. By the end of this session, you will be able to recognize why compressed air is the most expensive utility and where inefficiencies occur, identify major system components and their roles in performance, evaluate air distribution, storage, and air quality requirements, understand best practices for controls, leak management, and monitoring, estimate cost saving opportunities and leverage utility incentives, and a complete 10-question self-assessment to benchmark their current system. One thing I want to emphasize: this is not meant to be an advanced engineering training. Instead, this is an awareness level training that helps you recognize common problems and understand how they can connect to energy use, cost, and reliability. If you work in maintenance, operations, or engineering, this knowledge will help you spot issues early and prevent long-term waste. Compressed air is often called the fourth utility, after electricity, water, and natural gas. But there's an important difference. Electricity, water, and gas are typically metered. They show up clearly on utility bills. Their cost is visible. Compressed air usually is not. Instead, compressed air cost is hidden inside the electricity bill. There is no separate line item that says compressed air. And because it's hidden, waste can continue for years without being noticed. Here's the second key point. Compressed air is not only hidden, it's also one of the most expensive utilities in the facility. In fact, when you compare the true cost per unit of useful work, compressed air can require 8 to 10 times more electricity than directly using electric power. Why? Because compressed air is inherently inefficient. Most of the electrical energy becomes heat, only a fraction becomes usable compressed air. So we start with a thermodynamic disadvantage. Then, after we produce that expensive compressed air, we often waste it. Common inefficiencies include leaks, which can account for 20 to 40% of production, poor controls causing compressors to cycle inefficiently, pressure drop in piping and filters, excess system pressure, and inappropriate use like open blowing. There's also a simple but powerful relationship between pressure and energy. For every 2 psi or pound square inch of unnecessary pressure, energy consumption increased by roughly 1%. That means small pressure increases quietly at cost every hour this system runs. And most compressed air systems run continuously. Many facilities operate compressors 24 hours a day, even if production runs 1 or 2 shifts. So, waste doesn't just happen during production, it happens overnight, on weekends, during downtime. The continuous operation magnifies inefficiencies. So, this training is all about shifting mindset. Compressed air is not just a utility, it is a system, one that converts electricity into mechanical energy, and it must be actively managed. When managed properly, compressed air system reduces energy cost, improve reliability, and strengthen overall operational performance. And that's why managing compressed air saves money. This slide shows one of the most important relationships in compressed air systems. Power usage does not always match useful air consumption. If you look at the bottom of the graphic, you will see that when we consume electricity in a compressor, roughly 85% of that energy becomes heat. Only 15% becomes usable compressed air energy. That means compressed air starts off with a major efficiency disadvantage. Now look at the green section at the top. The air delivered by the compressor is divided into several categories. Production, which is a useful portion, leaks, air artificial demand, inappropriate use. Only the production portion creates value. Everything else represents waste. In an ideal system, if air demand drops, energy consumption should drop proportionally. Less airflow should mean less power draw. But in real facilities, that often doesn't happen. You may see high power draw even when useful airflow is relatively low. Why? First, many compressor operates in a load-unload mode. Even when unloaded, not delivering air, they can still consume 60 to 80% of full load power. Energy use stays high even when demand falls. Second, systems frequently operate at higher pressure than necessary. Higher pressure requires more energy to compress the air. It also increases leak flows and create artificial demand. Tools and processes consume more air simply because pressure is higher. Third, poor controls and poor sequencing between multiple compressors can create inefficiencies. Instead, one of compressors running inefficiently at full load, you may have multiple compressors partially loaded, cycling, or even competing against each other. That results in higher total power for the same airflow. The key takeaway from this slide is this. You cannot manage compressed air efficiencies by looking at pressure alone. Pressure might look stable, production might be running smoothly, but energy could still be significantly higher than necessary. To truly understand performance, you must evaluate airflow, compressor loading behavior, and power consumption together. When those three are aligned, the system operates efficiently. When they are not, waste remains hidden. Now that we understand why compressed air is expensive and inefficient by nature, let's look at how the system actually works. Here you can see a full compressed air system, from ambient air intake all the way to end use. Let's walk through it step by step. On the far left, we begin with ambient air intake and pre-filtration. The compressor pulls in atmospheric air, which already contains moisture, dust, and contaminants. Pre-filtration protects it from ingesting debris. Next is compressor itself. In the example, a screw compressor. This is where electrical energy is converted into compressed air energy. As we discussed earlier, most of the energy becomes heat during compression. From there, air typically enters a wet receiver with a condensate drain. When air is compressed, its temperature rises. As it cools, moisture condenses. The wet receiver helps separate and remove that condensate before air moves downstream. Then we move on to the air treatment, which may include dryers to remove moisture, filters to remove particulates and oil, additional drains to remove collected condensate. Air treatment is essential. Without it, moisture, oil, carryover, and particles can damage equipment and reduce product quality. After treatment, air usually enters a receiver tank, sometimes called dry storage. Storage serves several important purposes. It stabilizes system pressure, it reduces compressor cycling, it absorbs short-term demand spikes, and it improves overall control performance. From storage, air flows into distribution network, the piping system throughout the facility. Distribution design matters. Pipe size, layout, loops versus dead end, and maintenance all affects pressure drop, air quality, and system reliability. Poor distribution can undo the benefits of efficient compression and treatment. Finally, air reaches the point of use. At this stage, additional filtration or pressure regulation may occur before air powers tools, machines, automation systems, valves, and production processes. But air also reaches something else, leaks. Leaks are technically a form of demand, but they produce no useful work. They consume energy continuously, often 24 hours a day. And this leads to one of the most important message on this slide. Most compressed air waste happens after the compressor in distribution and end use. That's why managing compressed air cannot focus only on compressor room. It requires a system level approach from intake to end use. When every component is considered, compression, treatment, storage, distribution, and end use, the system becomes more efficient and more reliable. Now that we have seen that system from end to end, let's zoom into the heart of it, the compressor itself. On this slide, you can see three common compressor types. On the left is reciprocating compressors. This type uses piston similar to an engine to compress air. Reciprocating compressors are often used for small loads, intermittent demand, or specific high-pressure application. In the center is a rotary screw compressor. This is the most common type found in industrial facilities. It uses two intermeshing rotors to compress air continuously. Rotary screw compressors are well suited for steady, ongoing demand and typically used in majority of manufacturing plants. On the right is centrifugal compressor. These are used for very large systems. Instead of mechanically trapping air, they use high-speed rotating impellers to accelerate and compress air. They are common in large industrial or utility scale applications. Regardless of type, the core function is the same. The compressor converts electrical energy into compressed air energy. But the efficiency of conversion depends heavily on several factors: proper sizing, control strategy, operating pressure, and maintenance conditions. Compressors operate most efficiently when running at a stable load near their designed operating point. They operate inefficiently when they cycle frequently, spend long periods unloaded, or run at a high pressure than required. For example, an oversized compressor may meet demand, but it may constantly cycle on and off. That cycling wastes energy and increases mechanical wear. Similarly, increasing discharge pressure increases the work required to compress air, directly increasing energy consumption. Maintenance also plays a role. Dirty filters, fouled coolers, worn components, or improper lubrication all reduce efficiency over time. So when the compressor is a critical component, it does not operate in isolation. Its performance is strongly influenced by the rest of the system, including storage, controls, distribution, and end-use demand. That's why Compressed air must always be viewed as a system, not just a piece of equipment. With that system view in mind, let's start scoring our own, beginning with how well your compressors are sized. Are your compressors oversized? Use the 1 to 5 scoring guide shown on the slide. Oversizing is one of the most common problems in compressed air system. Facilities often oversize because they want capacity for growth or because they want to be safe. But oversized compressors can cause excessive unloading, unstable pressure, higher energy use, and more wear and tear. Even worse, oversizing often leads to the wrong control strategy. A larger compressor running in load-unload mode at low demand is extremely inefficient. The best practice is to size the compressor based on measured demand and use controls that match supply to demand. Take a moment and score your system from 1 to 5 based on this guide. Once sizing is right, the next place waste height is on the demand side and in the distribution. This is where many facilities lose the majority of their compressed air efficiency, not in the compressor room, but on the demand side. Let's start with demand. On the left side of the slide, you see peak versus average air demand. Most systems are sized for peak demand. In this example, around 300 standard cubic feet per minute, while average demand may be closer to 200 SCFM. That difference matters. If systems are designed only around peak demand without proper storage or controls, compressors may cycle inefficiently, and if inappropriate uses are present, such as open blowing for cooling or sweeping, demand increases without adding production value. Remember, demand includes everything that consumes air: tools, machines, valves, automation, process, and leaks. Now let's look at the distribution. In the center, you'll see a loop piping system. Loop piping provides two flow paths that reduces pressure drop and help maintain more uniform pressure throughout the facility, often limiting pressure drop to just 1 to 3 psi. On the right, you see a dead end piping system. Dead-end systems have a single flow path. As air travels farther from the compressor, pressure drops progressively, sometimes 7 to 15 psi or more. When pressure drop occurs, the common response is to raise the compressor discharge pressure. But increasing discharge pressure increases energy consumption across the entire system, not just at the problem location. That's why the message at the bottom of the slide is so important. Optimize the demand size before upgrading the supply. The biggest savings are often found by reducing inappropriate uses, repairing leaks, improving piping layout, and minimizing pressure drop. Compressed air efficiency is not just about buying a better compressor. It's about managing demand and designing distribution properly, because that's where many of the largest saving opportunity exists. Let's look at how is your distribution. Use the scoring guide shown again. A dead-end distribution system often causes large pressure drops. A looped distribution system reduces pressure drop and improves stability. Pressure drop is expensive because it forces higher compressor pressure. A 10 psi pressure drop in distribution is not uncommon in older systems, but it's a major waste driver. Improving distribution often involves adding loops, increasing pipe size, reducing restrictions, improving drop legs, and fixing poorly designed branch lines. Score your system based on the guides on the slide. Let's also score if your system is optimized. Optimization means the system delivers the right air pressure and flow with minimum waste. Key factor includes operating at a lowest practical pressure, having adequate storage, using stable controls, and using heat recovery where possible. Storage is often misunderstood. Storage is not backup air. Storage stabilizes the system and reduces cycling. A fully optimized system uses controls and storage together, so compressors do not chase short-term spikes. Score your system using the guide. Now that we have looked at how the system is set up, let's shift focus to what actually flowing through it: air quality. Let's look at what actually in that air. Compressed air is not clean by default. It naturally contains three primary contaminants: moisture, air, and particles. And even if we don't manage them properly, they directly impact both performance and uptime. Let's start with moisture. When compressed air cools, water condenses. If that moisture isn't removed, it can cause corrosion in piping, sticking valves, instrument failure, and in colder conditions, even freezing. In production environment, moisture can also damage product quality, especially in food, pharma, and electronic applications. Next is oil. Even oil-injected compressors allow small amount of oil to pass downstream. Without proper filtration, oil droplets and vapors can contaminate processes, damage pneumatic tools, and foul the equipment. Then we have particles, dust, rust, and pipe scales. These can wear down components, plug small orifices, and reduce overall system reliability. That's why air treatment equipment is critical. Most facilities use refrigerated dryers, which typically produce a pressure dew point around 37 to 50 degree Fahrenheit. That's suitable for many general industrial applications. For more demanding environments like critical pharma, food, or electronics, desiccant dryers are used to achieve much lower dew points. Air quality requirements are defined by ISO 8573, which classifies acceptable levels of moisture, oil, and particles, depending on the application. The key takeaway is this: not every process needs the same air quality level. Overtreating waste energy. Undertreating creates failure. So the goal is to match air treatment to process needs. Efficient air treatment doesn't just improve product quality, it reduces equipment failures, minimizes downtime, and strengthens overall system reliability. Air quality is both a quality issue and a reliability issue. Let's see how reliable your air treatment is. Score from 1 to 5. Air treatment includes dryer, filters, and drains. One of the most common hidden problems is drain failure. A drain stuck open wastes air continuously. A drain stuck closed floods the system. Filters also matters. Dirty filters increase pressure drop and energy cost. Dryers matter for both air quality and reliability. A best practice is to align treatment with required air quality standards such as ISO requirement and maintain it consistently. Now score your system using this guide. For treatment, let's shift to how we actually actively manage the system: controls, audits, and efficiencies. This section is about how we actively manage compressed air system rather than simply reacting to the problems. First, let's talk about controls. Compressors typically operate using start, stop, or load, unload control strategies. These methods work, but they can be inefficient if system demand fluctuates frequently. More advanced systems use variable speed drives or VSDs, which adjust motor speed to better match real-time demand. When applied correctly, this can significantly reduce energy consumption and stabilize system pressure. Now let's talk about waste, especially air leaks. Leaks are one of the largest source of energy loss in compressed air system. In many facilities, 20 to 40% of compressed air is wasted due to leaks. And remember, compressed air is one of the most expensive utilities in a plant. So leaks are not just small annoyances, they are continuous energy drains that run 24/7. This is where audits come in. A simple walkthrough assessment can identify obvious leaks and control their issues. Trend logging, monitoring pressure, flow, and kilowatt provides low-cost insight into the system performance over time. And a full compressed air audit offers deeper analysis to quantify losses, optimize controls, and right-size the equipment. Without controls and data, compressed air system becomes reactive. We only respond when pressure drops or equipment fails. With proper controls and auditing, we can proactively identify waste, maintain stable operation, and capture some of the largest energy savings available in a facility. Controls plus audit equals efficiency. This slide introduces efficiency metrics. Efficiency is measured by much more than pressure alone. Pressure matters, but it doesn't tell the whole story. To truly understand performance, we look at several key metrics: pressure stability, flow, energy use in kilowatts, compressor loading behavior, and leak rate. But ultimately, all of these roll up into one core question: how much energy does it take to produce useful compressed air? On the left side of the slide, you can see system performance, often expressed as delivered air per kilowatt consumed, measured in CFM per kilowatt. But oil lubricated screw compressors, it is 5 CFM per kilowatt or higher, is considered excellent. 3 to 4 is good. Below that suggests inefficiency and opportunity for improvement. This metric tells us how effectively the entire system converts electrical energy into usable air. On the right side, we look at compressor performance, often expressed as specific power measured in kilowatt per 100 CFM. For example, a single-stage oil-lubricated screw compressor may range roughly from 16.7 to 20 kilowatt per 100 CFM. A two-stage compressor is typically more efficient, around 15.6 to 16 kilowatt per 100 CFM. Lower specific power means better efficiency, less energy required to produce the same airflow. You will also see the term isentropic efficiency, which relates to how closely the compressor approaches ideal thermodynamic performance. While more technical, it reinforces the same idea: minimizing energy losses during compression. The key takeaway is this: efficiency is not a guess, it's a measurable. When facilities track pressure, flow, and power together and trend the data over time, inefficiencies become visible. Oversized equipment, poor controls, excessive leaks, and unstable loading pattern all show up in the data. And this leads to the simplest principle on this slide: if you don't measure it, you can't manage it. Facilities that consistently measure and trend these values identify waste quickly and sustain savings long term. Measurement turns compressed air from hidden utilities into a managed system. Now let's see what these principles look like in real facility. This slide shows an example case study from a precast concrete facility in northern Washington. Before the project, the facility was operating a 60 horsepower fixed speed load-unload rotary screw compressor. Like many facilities, they were experiencing common issues: higher than necessary pressure set points, frequent cycling, meaningful air leaks, and limited system monitoring. These conditions are very typical. The system runs, production continues, but energy performance is far from optimized. After evaluating the system, the facilities implemented several improvements. They replaced the fixed speed compressor with a 50 horsepower variable speed rotary screw compressor, better matched to actual demand. Let's look at the numbers. First, notice that the average flow remained essentially the same, about 21 to 23 CFM. That tells us production demand did not change significantly. However, look at the average power consumption. Baseline power was 14.22 kilowatt. After upgrade, verified power dropped to 4.96 kilowatt. That is dramatic reduction in energy input while delivering similar airflow. Now look at compressor efficiency measured in CFM per kilowatt. Baseline efficiency was 1.49 CFM per kilowatt. After the project, verified efficiency improved to 4.27 CFM per kilowatt. That's nearly a threefold improvement in how effectively electrical energy is converted into compressed air. When we translate that into annual energy use, baseline consumption was 124,600 kilowatt hour per year. Verified post-project consumption dropped to 43,457 kilowatt hour per year. That results in approximately 81,000 kilowatt hour per year in verified energy savings, or about 65% reduction in energy use. In cost terms, that equates to roughly $6,000 per year in savings from a single system improvement. And remember, this does not include secondary benefits such as improved pressure stability, reduced compressor cycling, lower maintenance stress, and extended equipment life. This case study highlights a key lesson. Most compressed air systems are not dramatically oversized, but they are simply mismatched and poorly controlled. By repairing leaks, reducing pressure, improving controls, and matching compressor capacity to actual demand, facilities can achieve sustainable energy savings while improving reliability. This example sets up for the next discussion, where we will look more closely at pre and post project performance trends and what those improvements look like in real operating data. This slide shows the pre-project condition using a 60 horsepower load-unload rotary screw compressor. At the first glance, the system looks normal. Pressure is maintained and demand is met. But the trend data reveals inefficiencies. Across the top of the graph, you can see the pressure line hovering around 118 psig. The system is holding pressure, but notice how tight and receptive this cycling pattern is. The pink bars represent compressor output and the red line shows total power. What stands out is the frequent load and unload cycling. The compressor repeatedly ramps between load and unloaded states. Load-unload control is common in fixed-speed compressor and works well at full load. But at part load, the compressor still draws significant power even while unloaded. That's one of the biggest inefficiencies of load-unload control. When airflow demand decreases, energy consumption does not drop proportionally. At the bottom of the slide, you see some key performance numbers. Flow about 52 CFM, power 36.8 kilowatt, efficiency is 1.42 CFM per kilowatt. That efficiency level is quite low for a rotary screw compressor. It tells us the system is using a lot of electrical energy to produce relatively modest airflow. You can also see the instability in the rolling average flow. Demand fluctuates throughout the day, but the compressor response is binary, either fully loaded or unloaded. It cannot smoothly adjust output to match real-time demand. This constant cycling has two impacts. First, it wastes energy. Second, it increases mechanical wear. Contractors, valves, and internal components cycle repeatedly, which can shorten equipment life and increase maintenance costs. So the key takeaway from this pre-project condition is this. The system is meeting demand, but not efficiently. Without proper controls, right sizing, and ability to modulate output, the compressor wastes energy even when production demand is relatively low. This sets the stage for the post-project comparison, where we will see what happens when capacity and controls are better matched to actual system demand. This slide shows the post-project conditions after replacing the 60 horsepower load-unload compressor with a 50 horsepower variable speed or variable frequency drive, or VFD. The most noticeable difference is how much smoother the system runs. Looking at the graph, the blue line shows the system pressure, instead of tight, repetitive cycling pressure, is now more stable and controlled, operating around 108 psi, which is about 10 psi lower than before. That pressure reduction alone contributes to energy savings. The pink line shows total flow and the red line shows total power. Notice how power now tracks much more closely with airflow demand. Instead of jumping between load and unload states, the compressor adjusts motor speed gradually to match the real-time demand. That is the key advantage of a VFD. A VFD lets the compressor modulate output continuously. When demand drops, motor speed slows. When demand increases, speed ramps up. As a result, cycling is significantly reduced, pressure stability improves, and energy use becomes proportional to actual airflow demand. Now look at the performance numbers at the bottom of the slide. Flow remains about 52 CFM, especially unchanged from the pre-project condition. Power drops dramatically to 12.7 kilowatt. Efficiency improves to 4.1 CFM per kilowatt. Compare that to a previous efficiency of 1.42 CFM per kilowatt. This represents nearly a threefold improvement in how efficiently electrical energy is converted into compressed air. Just as important, the system is operating with less mechanical stress. Reduced cycling means fewer load-unload transitions, less wear on valves and contactors, and potentially longer equipment life. Now it's important to clarify something. A VFD does not automatically solve every compressed air problem. If leak remains large, if pressure is set too high, or if compressor is oversized, inefficiencies can still exist. The real takeaway is this. When equipment, size, and control strategy are properly matched to actual system demand, energy consumption can drop dramatically while reliability improves. This slide demonstrates what optimized performance looks like in real operating data: smoother, more stable, and significantly more efficient. Those efficiency gains, of course, depend on keeping waste out of the system, which brings us to leaks. With that, how well do you manage leaks? Leaks are often the number one waste source. Many facilities have leak rates of 20 to 30%. Some are even higher. Leaks waste air continuously, even during downtime. They increase compressor runtime and energy use. They also increase wear on compressors, dryers, and filters. A strong leak program is continuous, not a one-time. It includes regular surveys, repairs, verification, and ongoing awareness. Now score your leak management using this guide. Next question is, do you monitor pressure, flow, and energy use regularly? Monitoring is how you detect demand creep, system drift, and nighttime waste. Spot checks are better than nothing, but they often miss patterns. Regular monitoring and benchmarking allow you to track improvements over time. Continuous monitoring is best practice. It enables KPIs and early detection of inefficiencies. Score your monitoring approach. Now let's connect what we measure to what it actually costs and where utility incentives can help. One of the most important concepts on this slide is life cycle cost. When you look at a compressed air system over its lifetime, 70 to 80% of the total cost is energy, not the initial equipment purchase. That means small efficiency improvements can generate significant financial returns, especially since most systems operate thousands of hours per year. This is why compressed air projects often have strong payback. Reducing leaks, improving controls, adding VSDs, or optimizing system pressure can quickly lower energy consumption, and energy is the largest cost driver. In many regions, utilities also offer incentives and rebates for upgrades such as variable speed drives, leak detection, and repair programs. Advanced controls. These incentives help reduce upfront cost and accelerate return on investment. But savings don't last without maintenance. A strong preventive and predictive maintenance strategy protects both reliability and efficiency. That includes maintaining filters, ensuring drains operate properly, monitoring oil condition, and regularly checking for leaks. When filters clog, pressure drop increases and compressors work harder. When drains fail, moisture builds up and damages equipment. When oil degrades, efficiency declines. So, maintenance is not just about avoiding breakdowns. It is about sustaining energy savings over time. The bottom line is this: projects often pay back quickly, but maintenance sustains those savings. A well-maintained compressed air system is both more reliable and more efficient. Let's answer this question. Do you have a preventive maintenance program? A reactive maintenance approach leads to unexpected downtime, higher energy cost, and equipment degradation. Preventive maintenance improves filter condition, dryer performance, control reliability, and compressor efficiency. Predictive maintenance adds additional value by detecting issues early. Now score your maintenance program using this guide. The next question is, do you evaluate your life cycle cost and use incentives? Many decisions focus only on purchase price, but the life cycle cost is dominated by electricity. Utilities often offer incentives for leak repair, control upgrades, VSD compressors, heat recovery, and system audits. A best practice is to evaluate total cost of ownership and include incentives in the business case. Now let's score your approach. Now we move on into awareness and sustainability. Compressed air efficiency is not just about saving energy. It directly reduces electricity consumption, operating cost, and associated emissions. At the same time, it improves system reliability and production stability. But technology alone does not create sustained results. Sustained results, success depends on people. At the top of the slide, you will see a simple progression: audit, fix leaks, optimize, maintain, monitor. That sequence represents the journey of continuous improvement. An audit identifies waste. Leak repair delivers quick wins. Optimization improves control and system design. Maintenance protects the performance. And monitoring ensures gains are sustained. However, none of these steps last without leadership and culture. Operators and maintenance staff are on the front line. They are the ones who hear air leaks, notice unstable pressure, see drain failing, or recognize when set points are creeping upward. If unnecessary pressure increases become normal, energy waste becomes invisible. If small leaks are ignored, they multiply. That's why awareness is critical. When teams understand that compressed air is one of the most expensive utilities in the facility, behavior changes. The key benefits are clear: lower cost, improved reliability, and stronger sustainability performance. But these benefits are sustained only when efficiency is embedded into daily operations, not treated as a one-time project. The final message is simple. Efficiency is a journey, not a one-time event. When awareness, leadership, and consistent monitoring are in place, compressed air system delivers long-term savings and long-term reliability. That awareness starts with knowing the numbers. So let's look at the cost side next. Do you know your annual compressed air cost? Many facilities don't. Because compressed air is embedded in the electricity bill, the cost is often invisible. But even rough estimate helps prioritize improvements. Tracking cost regularly and including it in the KPIs is the best practice. Now let's score your cost awareness. The next question is whether inefficiency or efficiency tied to culture and sustainability goals. This question is about long-term success. If compressed air efficiency is not part of the culture, improvements fade. Leaks return, pressure creeps upward, monitoring stops, and energy waste returns. When efficiency is embedded in the culture, staffs are trained, awareness exists, and performance is sustained. Now let's score your system. Before we close, let's challenge the 5 beliefs that keep system inefficient. This slide highlights the top 5 compressed air myths. These myths are common and sound reasonable, but they often keep facilities from improving performance. Myth number 1: higher pressure equals more reliability. Many facilities raise pressure to solve problems. If a machine struggles, the response is often to bump up the set point. But every 2 psi increase adds roughly 1 to 2% more energy. It can also increase leak and wear. True reliability comes from fixing root causes and not masking them with pressure. Myth number 2: storage is backup air. Air receivers are often thought as reserve supply, but storage is primarily for stabilizing demand fluctuations, not replacing compressor capacity. If storage is being used to compensate for undersized equipment or poor controls, the system design needs a review. Myth number 3. Leaks are small. Individually, leaks seem minor, but collectively, they often account for 20 to 40% of total air production. And unlike production demand, leaks run 24 hours a day. Ignoring leak is like leaving lights on in every room all the time. Myth number 4. A VSD solves everything. Variable speed drives are powerful tools, but they're not magic. If the compressor is oversized, if pressure is too high, or if leaks are excessive, energy waste will still occur. Technology must be paired with proper system design and control strategy. Myth number 5, we already optimized this. Compressed air system change over time. Production shifts. Equipment is added. Leaks develop. Set point creeps upward. Optimization is not permanent. It requires monitoring and reassessment. These myths persist because compressed air is often treated as a background utility, out of sight and out of mind. But the best performing system challenges assumptions. They use measurements, audits, and data to verify performance. They fix leaks regularly. They control the pressure intentionally. And then they commit to continuous improvement. The bottom line is this: efficiency is not achieved by belief, it is achieved by measurement and disciplined system management. So if you scored lower than expected today, one or more of those myths may be influencing your system. Everything we discussed today, from leaks to pressure to controls to culture, ultimately comes down to one thing: measurable performance. Take a moment and total your score out of 50. This isn't a test, it's a snapshot. If you scored between 40 and 50, you're performing well. Focus on sustaining and refining. If you score 25 and 39, you have a solid foundation, but meaningful savings are still available. If you scored below 25, there is a significant opportunity and structured improvement should be a priority. No matter your score, the path forward is the same: audit, fix leaks, optimize, maintain, and monitor. Even strong systems drift over time. Without monitoring and discipline, inefficiency quietly returns. Compressed air management is not a one-time project, it is a continuous management practice. This brings us to the Q&A. If you're watching this as a recording, pause here and write down questions about your facilities. For example, do we know our leak rate? Do we know our pressure drop? Do we know our annual cost? Do we monitor flow and energy? Then follow up with your facility lead or energy team to decide on the next step. With that, I conclude my training. Thank you.